Okay, so we're going to start talking in 5-6 about something called substitution method. And what this basically does is we're going to have a theorem based off of this. And the substitution method theorem says if capital F prime of x is equal to little f of x, then we get the following thing happening. The integral of f of some u of x, u prime of x dx is equal to f of u of x plus c. So basically, if you look at this, this is trying to integrate something that's based off the chain rule. So what the substitution method is going to do is try to set up an integral where we convert it out of the chain rule form to a form with u's in it that we're able to go through and calculate. So I think the best way to learn this one is just to go through and do a bunch of examples. So we'll just kind of do the book examples here and then go from there. So it gives us the integral of 3x squared sine of x cubed dx. So when we go to use the u substitution method, what we do is we look and see what's kind of the inside part of it. So basically, we're trying to undo the chain rule. So we're going to say, like, in this case, we're going to say sine's kind of the outer function, x cubed is the inner function, and then the derivative of x cubed is 3x squared. And we note we kind of got a 3x squared out there. So this is part of the inner derivative from the chain rule. So what we're going to do is we're going to try to set u equal to the inner function, which in this case is x cubed. Then to get du, we'll take the derivative of x cubed, and we're going to put a dx after it. So the derivative of x cubed would be 3x squared, and then we put a dx after it. So when you do the du, you take the derivative of u, put a dx afterwards, and then we're going to go and rewrite our integral in terms of u. So we're going to say it's the integral of sine of, not x cubed anymore, x cubed is u, and then 3x squared dx, the entire 3x squared dx just becomes du. So I still have the same thing. This is still sine of x cubed. We're just using u as a hold-in for x cubed. And then du, the symbol du, is 3x squared dx. So this right here is the same information as that. The main point is this is easier to integrate. So we think and say, okay, I got sine. What function, when I take the derivative of them, becomes sine? And that's negative cosine. So I have negative cosine of u. Since there's no limits on my integral, I have to put the plus constant. So we integrated our integral in terms of u. The original problem was in terms of x, so we need to go back to x's at this point. So now I just need to replace my u with an x cubed, and that will give me my answer. So we're going to look at another couple of these. So that's first example. Next, they're going to say, all right, for this example 2, what if we had the integral of x times x squared plus 9, all that to the 5th power, dx. So we're going to let u be sort of the inner part of the function from the chain rule. So we're going to let u be the whole x squared plus 9 since that's being raised to the 5th power. 5th power is kind of the outer function, and the x squared plus 9 is sort of our inner function. So we say, okay, to get du, I need to take the derivative of my inner part. X squared's derivative becomes 2x. 9 becomes 0, so I don't need to write it. And then I put a dx. So I have the dx, I have the x, I'm missing a 2. So what I need to do here is I need to bring a 2. I need a 2 in our function, so we get the 2x dx. But if I put a 2 there, it unbalances the equation. So to keep the equation balanced, since I'm adding a 2 in, I need to put a 1/2 out front. And then I can rewrite my integral in terms of u. So I'll get 1/2 out front integral of, instead of x squared plus 9 to the fifth, x squared plus 9 is u, so this will be u to the fifth. And then 2x dx, 2x dx is du. So I have the 1/2. I'm going to take the antiderivative of u to the fifth, which will be 1/6 u to the sixth. And I need to put a plus c after it because I've taken the integral and it's an indefinite integral, so we have to put a plus constant. 1/2 times 1/6 is 1/12. I need to replace u with what u actually is a stand-in for. U is a placeholder for x squared plus 9. So I'll put x squared plus 9 in for u. That's to the 6th power plus c. And that will be our integral, basically. Okay. So we're going to look at one more of these, or actually a couple more of these with indefinite integrals. Then we'll go through and we'll see what about if you have limits instead of no limits on the integrals. So let's look at the next one, example 3. So example 3 says we're trying to evaluate the integral, have a division. It looks like we got x squared plus 2x up top. Dx is up there as well. And in the bottom we have a x cubed plus a 3x squared plus a 12. And that's all to the 6th power. So since this is all raised to the 6th power, I'm going to view this as kind of my inner function for the chain rule. So I'm going to let u equal x cubed plus 3x squared plus 12. Then I'm going to need to calculate du. So the 3 comes down, I get 3x squared plus the 2 comes down, that's 6x. And then plus 12 goes away, and I get all that times a dx. Well, if I look here, the dx is there. I have 3x squared plus 6x, and here I just have an x squared plus 2x, so these don't match. What we want to note is if I factor a 3 out of this, this is 3 times x squared plus 2x dx. So my du is actually 3 times x squared plus 2x dx, and now it becomes a little more clear. I have the dx, I have the x squared plus 2x, so here's dx, here's x squared plus 2x. I need a 3, so I'm going to put a 3 up there. If I put a 3 up there, that unbalances the equation, so I need to put a 1/3 out front to keep the effect kind of balanced. So I have 1/3 integral of, let's see here, x cubed plus 3x squared plus 12. That is u, that's to the 6th power. So we'll have all that u to the 6th power. And then the top becomes, 3 x squared plus 2x dx. That is all the stand-in for du. So I'm going to rewrite this a little bit nicer. This is going to be 1/3. If you have u downstairs like that, it's 1/3 integral of u to the -6 du. So when we go to integrate that, we're going to say, all right, if I add 1 to -6, I get a -5. The -5 will come down, so I need a 1 over -5 to keep stuff balanced. Or rather, so when I take the derivative, it becomes the correct thing. And I put the plus c after it. So I need to say, all right, 1/3 times -1/5 is -1/15. I'm going to replace u with what u actually was a stand-in for, which was x cubed plus 3x squared plus 12. So x cubed plus 3x squared plus 12. All that's to the -5th power plus c. So this is our antiderivative using the u substitution method. Okay. So again, you have to kind of identify what's the inner part of the chain rule. So here we had all this stuff to the 6th power. So that was kind of the indicator that this stuff should be the inner part. And then we kind of had where this didn't match what we had there. So we had to look at that a little bit and said, oh, if we factor a 3 out, then we kind of recognize we have some of the same stuff. Still need to include a 3. When I include the 3, I need a 1/3 there. then the rest of this is kind of algebraically write it nicer for taking the integral, go through and take the actual integration, and then substitute what u actually was a stand-in for, substitute that back in for u to get your answer in terms of x's. All right, so next bit. This time they want us to do the integral of sine of 7 theta plus 5 d theta. So with this, sine is the outer function, 7 theta plus 5 is my inner function, so I'm going to let u be the inner part, 7 theta plus 5. So when I take the derivative, instead of getting a thing dx with dx at the end, this time we're going to get a d theta at the end because our variable is theta instead of x. So when I want du, 7 theta's derivative is 7, 5's derivative is nothing, so I have a 7 d theta. All right, so when we go to write this down, we have the d theta, we're missing the 7, so we need to put a 7 here. So we have a 7 times the d theta, and that means I need to put a 1/7 out front. So I have a 1/7 integral of sine of just u, because 7 theta plus 5 is u, and then 7 d theta becomes du. So I think, okay, who's the function when I take its derivative turns into sine of u? That would be negative cosine of u. Then I need to put a plus c after it. And then after I do that, I need to replace the u with what u actually equals in terms of theta this time instead of in terms of x. So I get negative 1/7 cosine of 7 theta plus 5 plus c. Okay. All right, so let's look at a couple more. So next up, what happens, how do you deal with one that has exponentials in it? So we have the integral of e to the negative 9t dt this time. So e is sort of the outer function, negative 9t is the inner function, so I'm going to let u equal negative 9t. Therefore, du, when I take the derivative of negative 9t, I get negative 9 dt. So I have the dt, I'm missing negative 9. So I put a negative 9 here. If I put a negative 9 in there, I have to put a negative 1/9 out front to keep everything balanced. And so now I have a negative 1/9 integral of e to the negative 9t is u, so that's e to the u. And negative 9 dt is du. E is its own antiderivative, so this will become negative 1/9 e to the u. I have to put a plus c after it. U is a stand-in for negative 9t, so this will be negative 1/9 e to the negative 9t plus c, and that should be our antiderivative. Sorry, that should be the indefinite integral that we're trying to calculate. Okay, got a couple other ones we need to look at, and then we'll see what happens when we have limits on our integrals. So for this example, they want us to take the integral of tangent of theta d theta. So at the moment, there's nothing really, kind of get stuck. So I'm going to say tangent, if we remember, is sine of theta over cosine of theta, and we have a d theta up here. So sine of theta is on the same level as the d theta. So if I can choose u so that my du is something sine of theta d theta, I can get this to work out and be able to do this integration with respect to u. So if I set u equal to cosine of theta, then du, if I take the derivative of cosine is negative sine of theta d theta. So I get the sine theta d theta, but I'm missing a negative. So I have to put a negative here, and if I put a negative there, we have to put a negative out front to keep the equation balanced. So when I do this, I get negative integral of, see, it's going to be 1 over cosine is 1 over u, and negative sine of theta d theta, I'm going to say negative sine theta d theta, that all is du, and I'll write that kind of off to the side. When you take the antiderivative of 1 over u, that is natural log of absolute value of u. And we have a plus c after it as well. And now we substitute back in what was u actually. U was cosine of theta plus c, and that will be our integral in this particular case. Okay. So here's one that's going to start out using u substitution. We're going to get stuck, and then we're going to have to kind of rearrange some stuff to get it to go through. So we have the integral of x square root of 5x plus 1 dx. So you'd start out and saying, by now we see like, okay, we kind of see that there's square root. This is the stuff underneath the square root, so we probably should choose that to be our u. So we'll say u is 5x plus 1. Then du would be just 5 dx. Let's take the derivative of 5x, that's 5. Derivative of 1's nothing. So we get 5 dx. Problem is, if I plug this in for u, and I bring in a 5, and I get 5 dx and make that du, I have an extra x left over. So what we can do that occasionally works in these is we can take this equation and we can start to solve it for x. So I'm going to subtract the 1 across. I'm going to divide everybody by 5. So u over 5 minus 1 over 5 is x. Over here I'm going to solve this for dx. So I'm going to say du divided by 5 is dx. So now I know what, so I'm going to kind of box these in. These are kind of intermediate steps. These aren't the actual answer. Don't know why I'm really using dotted boxes, but we're just going to say that's okay. So these are kind of important things, but they're not our actual answer. So what we're going to do is we're going to replace dx. We're going to replace the symbol dx with this. We're going to replace the two appearances of x's up here. We're going to replace those two x's with u over 5 minus 1/5. So when we do that, we get the integral of, it's not x anymore, it's u over 5 minus 1/5. That replaced the x. I have the square root of 5 times not x anymore. I'm replacing x is equal to u over 5 minus 1/5, so I'm replacing the x with u over 5 minus 1 over 5. And then I have a plus 1. And instead of dx, I'm going to use du over 5. Okay. So I'm going to start simplifying this down algebraically for a while. There's a 1/5 here I'm going to push up to the front. I'm going to push the 1/5 here up to the front as well. So if I remove the 1/5, that'll leave the u behind. If I remove the 1/5 here, that'll leave a 1 behind. The square root, if I let the 5 distribute, the 5 up here will cancel with the 5 down there. That'll just leave me with a u. The 5 here, 5 times 1, negative 1/5 will be a negative 1. We'll have a plus 1, and since this 1/5 I pushed all the way out there, we have a du. Okay, so next up, 1/5 times 1/5 is 1/25, and I'm going to push that out in front of the integral. You can push constants through the integral, so we're going to do that to make the leftover stuff a little bit easier to see. Minus 1 plus 1 cancel, so I have the square root of u, which square root of u is the same as u to the 1/2 power, and then out here I have a du. So I need to distribute my u to the 1/2 power, so I have 1/25 integral of u to the 1 times u to the 1/2. You add the exponents, that's u to the 3/2 minus u to the 1/2 du. And finally, we're in a form where we're ready to take the antiderivative. We're ready to calculate this indefinite integral. So we say, okay, if I add 1 to 3 halves, I get 5 halves. So that's u to the 5 halves. I'm going to need a 2/5 out front of the 5 halves so that whenever I take the derivative, it cancels out correctly. Then I get a minus u to the 1 half. That becomes u to the 3 halves. When you add 1 to 1 half, get 3 halves. So that needs a 2/3 out front. And then that needs a plus c. Final thing is I need to replace the u's with what u's actually equaled. U is 5x plus 1. So I'm going to distribute the 1/25. So I get 2 over 125. I already forgot what u was. U is 5x plus 1. So I replace the u with 5x plus 1. That's to the 5 halves power. Then we get 1/25 times 2/3. That's minus, let's see, 2 over 25 times 3 is 75. Replace u with 5x plus 1 to the 3 halves power plus c. So when you guys are solving these, only do this type whenever your choice for u and du. So like here we had u and du and we were able to get all the stuff, but you only really need to mess around with this if your initial, so I grabbed the inside thing and I had kind of this x that didn't get incorporated with the du. There was kind of this leftover x. That's kind of whenever you have some extra stuff in there, that's the tip off that you may want to try this. However, it's not guaranteed to always work. So if you try u substitution and it doesn't necessarily go through, this method here won't work every time. It's just, this is a possible way of getting unstuck is solve for x, solve for dx, substitute in for dx, and substitute in for the x's. And then you get an integral in u that you may be able to algebraically rearrange into something you know how to actually take the antiderivative of. So down here, we're going to look at what happens now if we have integrals that have limits on them. And we'll go through and take a look at a couple of these. So this is called the change of variables. Formula for integrals. So this says the integral, if you have integral of a up to b of some outer function evaluated at the inner function times the inner derivative of the inner function with dx. So basically you're trying to take the derivative of something that you could apply the u substitution to. This is going to equal to the u evaluated at the upper limit, u evaluated at the lower limit of f of u du. So you'll be able to, when we converted the indefinite integrals over to u, at the very end we had to go back to x's to write the answer in terms of x's. For a definite integral, when you convert it over to u, as long as you update the limits to the new u limits, you're able to, from this step here, just plug in and get your answer. You don't need to go back to the x's. So let's look at a couple examples that deal with this, and then we'll stop there. So this is example 8. This says we have the integral from 0 up to 2 of x squared square root of x cubed plus 1 times a dx. So sort of the inner function is the x cubed plus 1. That's underneath the square root. So I'm going to try to set u equal to that. If I do that, then my du, the derivative of x cubed is 3x squared. And then the plus 1 goes away, and we just have a dx. So it's 3x squared dx. So I got my x squared. I'm missing a 3, so I'm going to put a 3 out front. And I need a 1/3 out here to balance out the fact I put a 3 there. So when I go through and do this, I get a 1/3 integral from 0 up to 2. Okay, I just messed up because I'm going to go through and I'm switching over to u's. So I need to update my limits here in just a second. So we'll say this is square root of u, because u is x cubed plus 1. 3x squared dx, 3x squared dx is du, so that's there. And then we need to make our new limits. So I take 0, and I'm going to plug 0 in for the x in my expression here and figure out what u value that generates. So 0 cubed is 0, plus 1 says I get 1 for my new limit. Then I take 2 here, I substitute 2 in for x right here. So again, just to make it clear, this is where I'm substituting the 2 in for x here and seeing what does it make that equation. 2 cubed is 8, 8 plus 1 is 9, so my new limit, that's upper limit, is 9. So whenever everything's in terms of x's, your limits are 0 to 2. Whenever everything's converted over to u's, you use this little equation here to figure out, if I put 0 in for x, what does that mean in terms of u? If you put 0 in for x, you get 1 for the lower limit. Put the upper limit 2 in. 2 cubed plus 1 is 9. That gets you the new upper limit. And I'm going to rewrite the square root in terms, so I'm not doing any calculus right here at this point yet. I'm just going to rewrite this in terms of a power so it's easier for me to take its antiderivative. So I say, all right, I have a 1/3 out front. Now I'm ready to integrate. I'll have a u to the 3/2. And then if I have a u to the 3/2, I need a 2/3 out front. And this is all evaluated from 1 up to 9. So I have 2/9 u to the 3/2 evaluated from 1 up to 9. So to finish this off, we'll say, all right, this is 2/9 evaluated at 9 to the 3/2 power minus 2/9 times 1 to the 3/2 power. I guess I probably should put parentheses in there just to keep stuff clean. All right, 1 to the 3/2 power is 1, so this whole term here is just going to be 2/9. This says take the square root of 9, which is 3. Square root of 9 is 3. 3 cubed is 27. And so I have basically 27 times 2. 27 times 2 is 54. So I have 54 over 9 there. And 54, if I divide 54 by 9, let's see here, 54 divided by 9 is 6. So I have 6, or you know what, actually let's do it this way. This is already in terms of ninths. So 54/9 take away 2/9 is 52/9. So yes, 54 divided by 9, that is 6, but then you have to do 6 minus 2/9, so you have to convert it back to 54/9 anyways. So we have 52/9 for our answer to that one. So start out with x information, start converting over to u. Make sure to convert the limits to your new limits as well. And then you can solve this thing in terms of u, and you use the new u limits, and you don't need to go back to x's. All right, so moving along here for the next example. We get the integral of 0 up to pi over 4. And we're going to have a tangent cubed of theta. And this is going to be times secant squared of theta d theta. So tangent cubed, I'm keeping a couple things here. The derivative of tangent is secant squared. So I'm going to try to choose tangent as my u. Because then when I do du, derivative of tangent is secant squared theta d theta. I get the secant squared theta d theta. That actually is going to get wrapped up as du. So I'm going to need my new limits of integration. So I'm just going to put an integral sign there. I get u cubed, and then secant squared theta d theta becomes du. Okay, if I put 0 in, tangent of 0 is 0. If I put pi over 4 in, tangent of pi over 4 is 1. So these are my new limits. This turns into, when I integrate u cubed, that's u to the 4 with a 1/4 out front. And we're going to evaluate that from 0 up to 1. So this will be 1/4 times 1 to the 4th minus 1/4 times 0 to the fourth. A fourth times 0 to the fourth, that whole term goes to 0. 1 to the fourth is 1. 1 times the fourth just says we get a fourth back from that one. Okay. So last example here we're going to do from this section, and we'll stop there. For this final example, I want us to find what is the area under the graph of y equals x over x squared plus 1 over the interval 1 up to 3. So it wants us to find the area under that curve over the interval 1 up to 3. So we would set up the integral from 1 up to 3, because that's the interval they told us they want us to find the area under. We're going to put down our function x over x squared plus 1, and we'll say dx. And this will calculate basically whatever this graph looks like. This will calculate the area. It's actually the signed area underneath it, which the way they've phrased the problem, that's what they're wanting us to do. So I'm going to try to make u the bottom here. So u equals x squared plus 1. Then hopefully du. Derivative of x squared is 2x. Derivative of 1 is nothing. And then I have to put a dx after it. So I have the x dx part, but I'm missing the 2. So I will put a 2 there and put a 1/2 out front. And then this will become, let's see, start converting this over to u's. So it's 1/2. We'll get some new limits here in just a minute. 2x dx is du over x squared plus 1 is just u. To get my new limits, I put, I'm going to basically into this x squared term here, I'm going to plug 1 and then 3 into that. So I get 1 squared, which is 1, plus 1, which is 2. Then I get 3 squared, which is 9, plus 1. 9 plus 1 is 10. So when I take the antiderivative of this, I get 1/2. Du over u turns into natural log of absolute value of u. That's going to be evaluated from 2 up to 10. So I get 1/2 natural log of absolute value of 10 minus 1/2 natural log of absolute value of 2. And then I can put that in calculator. So let's see, or if it's in the non-calculator portion of the AP test, you would just leave your answer like that and say that's as far as I can go without a calculator. If it's in a calculator portion, you could type this in, and we'll approximate it to 3 decimal places. So this will be about 0.805, really 0.80478, etc. But we'll say that's about 0.805, and that should pretty much wrap up section 5-6. So it's mainly just focusing on this u substitution method and how to use it if there's no limits and how to use it if there's limits on your integration. So I'll stop there.